Hi everyone. This work presents a case study on room acoustic solutions for social gathering places. In this presentation, we will first describe the space that was chosen as a case study, as well as the overview of the work. We will then talk about the model calibration, which was done using numerical simulations. That will bring us to talk about the metamaterial design and manufacture process. Finally, the simulation results performed to verify the newly designed acoustic treatment will be presented. The present case study focuses on the front dining area of a small-sized restaurant located in the city of Eindhoven, in the Netherlands. The studied space can accommodate around 12 to 16 people. The problem of this space is the poor speech intelligibility, which is mainly due to too high reverberation time, especially in the frequency range of 500 Hz to 1 kHz. To reduce the reverberation time, this work proposes a new acoustic solution to treat the space based on a metamaterial lamp design manufactured using 3D print. Here is how this work was decomposed. First, based on the data extracted from in-situ acoustical measurements, a digital twin of the space was created using numerical simulations. Numerical simulations involve two different solvers, one using the fast multiple boundary element method and another using the finite difference time domain method. Those two solvers were used to verify each other on the simulation results first. Obtaining and using the digital twin, it was then possible to investigate different acoustic treatments and their efficiency in reducing the reverberation time. More specifically, the dimensions, target frequencies, and impedance of an efficient acoustic treatment could be estimated using the digital twin. These parameters were then used as input for optimizing the metamaterial design. Based on those numerical inputs and manufacturer constraints, a metamaterial lamp was designed. The final design of this lamp was evaluated in the digital twin to verify its performance in reducing the reverberation time. A laser sintering 3D printing technique was finally used to manufacture the complex shape of the metamaterial lamp, which in the end combines aesthetic with high acoustic absorption. As mentioned before, the first part of this work focused on the creation of the digital twin of the space. For that aim, the 3D model of the space was created and simulated using both the finite difference time domain method and the fast multiple boundary element method. The correctness of the simulation results was first verified by comparing the outputs of the two numerical solvers in both time and frequency domains. Considering the high efficiency of the time domain simulations, the finite difference time domain method was used to calibrate the material properties of the model according to the measured reverberation time. More specifically, the calibration process consisted of adjusting the surface impedance of the materials constituting the room such that it corresponded to the measured reverberation time at each third octave band. The range of the variation for each material impedance was defined by available databases for absorption coefficients such that the calibrated values were realistic. After calibration, the reverberation time in the digital twin was the same as the measured one. Dimensions, target frequencies, and impedance were then provided as input for the optimization of the metamaterial design.
Hello, my name is Zhang. As my colleagues just mentioned that the goal is to acoustically treat the restaurant. Here, a metamaterial lamp design will be introduced, which will be later used to serve that need. To simplify the problem, instead of studying the lamp as a block itself, we just concentrate ourselves on a plate, which can be later used to assemble together to form the block. The design has a patch where multiple ducts are combined together as shown in the figure to the right. You can see that each duct has a resonance frequency, and by combining multiple ducts of different geometries together, multiple resonances can be induced. And so that means the absorption coefficient and the impedance can be changed arbitrarily. An analytical model is derived to predict this one. In order to validate the correctness of the model, two designs of different geometries are predicted using the analytical model, and they are also simulated in the numerical software. Where figure here shows the absorption coefficient of those two cases. As can be seen, for two cases, a very good match is found between the simulation and the analytical model. So this means we have fairly confidence in our analytical model. Next, an optimization is conducted based on the analytical model to maximize the absorption coefficient within 500 Hz to 1000 Hz. And the geometries of each duct are optimized just to serve that need. The patch size is set to be 30 centimeters by 30 centimeters. There are 15 ducts in total. And here it shows the absorption coefficient of the optimized structure. As can be seen from the figure, the absorption coefficient is very high throughout the frequency from 500 Hz to 1000 Hz. All right, so here we show a design that can achieve a high absorption within this frequency range. But you can also see that it's a patch composed of strict ducts. That means it will be very long and bulky. So in the next part, my colleague would give you an introduction on how to fold those ducts smartly in the space in order to achieve a more compact design. Thank you very much for your attention.
Hello, I'm Timur. Indeed, as my colleague said, ducts were folded inside of a lamp to allow have a compact design. On this picture you can see several types of folding algorithm which were used during design of the lamp. After ducts folding, next step was to position them in the volume of the acoustic metamaterial lamp. Assembly and positioning should allow to use most of the space inside of the lamp and at the same time leave some cavities for the light. Design and iteration of ducts assembly were done in Rhinoceros software using Grasshopper plugin. On these pictures, you can see several iterations of lamp design before we came up with the last design, which allows best acoustic performance as well as optimal manufacturability with using 3D printing technique which is called laser sintering. This 3D printing technique allows to produce parts with high resolution and without adding any supports during fabrication. Here you can see an animation of this slice geometry of the lamp, which can be laser sintered layer by layer until we have our final prototype of demonstrator. Thank you very much for your attention.
After the design of the Metamaterial lamp, we are curious to know its performance. Would it achieve the desired improvement for our room? Unfortunately, we're not able to verify this in the real restaurant at the current moment, but we can already test it with our reliable digital model. We can use fast multiple band to simulate the room with and without the new treatment for the target frequency range. Here we can take a close look at the comparisons at 800 Hz, 850 Hz, and 900 Hz. The top three plots are from the original room, while the bottom plots are the room with Metamaterial lamps. As shown by the simulations, many of the high modes are mitigated by the new treatment. We can also average the sound pressure level at different heights in the room. The top plot is a linear average of sound pressure level at 1.2 meter, which represents a scenario when people sit. We observe that the new metamaterials provide a maximum 16 dB reduction and an average of 2 dB reduction over the target frequency band. The bottom comparison is a linear average of sound pressure at 2 meters height, which represents a scenario when people stand in the room. The new metamaterial provides a maximum of 20 dB reduction and an average of 3 dB reduction over the target frequency band. In both scenarios, the metamaterial shows good performance considering its small volume compared to the room. Then the reverberation times are computed based on the simulation results for each third octave band. Significant improvements can be observed from the metamaterial lamps. For all the 4 target third octave bands, the new metamaterial lamps reduce the reverberation time by approximately 50%. If we look up the diagram of the verbal communication, the reduction of the reverberation time improves the verbal communication in the restaurant from insufficient level to sufficient level in many scenarios. The Metamaterial lamp provides a new acoustical treatment in social gathering places like restaurants and cafeterias. There are several advantages considering Metamaterial lamps. First, the design is very adaptive and can be customized to different spaces. The dimensions of the Metamaterial are designed based on the characteristics of the room. The exterior design of the lamp can be adaptive to the customer's taste, and the number of the Metamaterial lamps can be adjusted based on the requirements in the room. Secondly, the Metamaterial lamps are easy for installation and replacement. Additionally, it provides aesthetic appearance which can be attractive for customers. Some future work shall be done regarding the experimental validations of the Metamaterial lamps, and in-situ measurements for verifying the performance of the Metamaterial lamps in the real room. In the end, we'd like to acknowledge Marie Curie, Acoustic, and PBMV2 projects for the support of this research. Thank you so much.